today
It's really like a basketball.
we get to talk about landslides. Okay, so we're going to talk about landslides today, specifically landsliding versus slope stability. Sometimes we'll just call it determination of slope stability. The basic question is this: if I've got some kind of earth material that's sitting on kind of a steep slope, and say I've got a bunch of rainfall, and the question then is, of course, does it go or does it not go? Or in the immortal words of Sir Laurence Olivier, is it safe? Marathon man, anybody? No? I don't know, this whole, if you haven't seen it, you'll never, if you haven't seen it and you go see it, or you see it, whatever, you'll never view dentistry quite the same ever again. All right, rather than explain the plot of Marathon Man, I think I better get on with things. So, this question can get complicated, but we're going to consider a case that is simple enough for us to do something that's still not irrelevant, right? It's simple enough to do. It's not so simple that it's, it takes some good stuff into account. So that is, we will incorporate some important elements of realism. So let us consider a slab of, or a layer of mobile regolith on top of bedrock. Sorry. So this rock, let's bring it, etc. Here we've got our soil layer. Let me go ahead and draw up a coordinate system. X will be downslope parallel to the slope. We have some slope angle theta. Z will be normal to the slope, and Y goes into the board. All right. And as usual, we will do what we can to get rid of Y and neglect that. Okay. So, what are the forces on this slab? Well, it's got mass, right? So therefore, well, it's got mass, and we're on a planet with gravity, a universe with gravity. So, okay, we got weight, right? We've got a weight force. And so let's see, let's just sort of break out a portion of this material here, and for the time being we'll sort of try to consider, talk about it as if it's a point mass. We'll have to jettison that at some point, but my weight is W here. Anybody actually see that? All right. So we've got the weight. It points towards the center of the Earth in general, and it's equal to the mass times the acceleration due to gravity. And it goes downward, of course, so if I'm writing things all vector-y, then the weight vector is the mass times the gravity vector, and I can decompose that into components that are parallel to the slope normal direction and components that are parallel to the slope parallel direction. Okay, so that is my vector here is the mass times the magnitude of the gravity times sine theta in the x direction. Familiar maybe with this? Unit vector in the x direction minus cosine of the slope angle in the z unit vector direction. Okay. So, you know, being all rigorous here, because I know Mikhail will call me on this if I don't. You know, so there's our gravity vector, our weight vector, I mean. Okay, normal force, going to do it right this time. Which way is the normal force point? Well, it's the force, if we're considering this slab-o stuff on top of the bedrock, then it's the force that acts in the slope normal direction, and it's the pushback for gravity. It's what keeps things still in our z direction. So draw it, and it's going to be equal and opposite to the normal, the slope normal component of the gravity. Okay, so that just means that it's equal to weight times cosine of the slope angle. Okay, but the slope normal component of the weight. So, oh no, well, yeah, already, that's it, right? Okay, so normal force equals mg cosine theta in the z with the z unit vector. Okay. No. Yes. Wait. Yes. The z. See, I confuse myself. Made my, you know, sometimes I'll forget that I've made my coordinate system convenient for me. All right. All right. What else then? I mean, we've kind of taken care of what's keeping the mass from zooming towards the center of the Earth or flying off into space, but yeah.
Friction.
Yeah, friction. So clearly, I've already indicated that I've got a component of the weight that's pointed downhill. We kind of know that intuitively, right? Yeah.
Do you have to include the z in the mg cos theta z, because isn't cosine kind of denote that you're thinking about the z direction anyways?
Well, sure, and I'll dispense with vectors when I can, but in this case, they're not. It's not redundant information. This is telling me that in the z direction, which is slope normal, the amount of gravity is reduced by the factor of cosine theta. So my friction, this is one of the places where it can get a little bit complicated if we let it. So this is going to be opposite my downslope direction, because friction is going to counter, friction is what's going to counter motion if there were going to be motion. So now, where are all the thing is, okay, I've drawn it, you know, as if it's just sort of, well, I've drawn it as two-dimensional on a chalkboard, right? But we know in reality that we're going to have friction wherever, if we have this slab that is, say, you know, actually has some depth to it. If it's going to move, it's going to have to slide against its base, it's also going to have to slide against its sides, because unless it goes infinitely in the y direction. But we're kind of going to pretend that it does go infinitely in the y direction, because that lateral friction is awfully inconvenient. And so we are going to neglect that. So we're going to neglect the sides and just talk about at the base. So that's one of our first simplifications. All right. So the friction at the base is a fraction of the normal force, but acting in the minus x direction. I messed it up in my notes, but so if I have a friction force, it's going to be a fraction in the negative direction, negative fraction of the normal force, but in the negative x direction. Okay, so just being explicit here for now at least, that taking my vector normal, taking the magnitude of it, multiplying it by a friction factor, friction coefficient, and it's acting opposite that downslope direction. Okay, let's leave that at that for now. Write this up here, leave myself a little room down here. Okay. What other kinds of forces might we have, especially the way I've drawn it? Now, let me draw my friction on here. Yeah.
Maybe a force of the soil above.
Yeah, exactly. I'm going to have some pressure force, which I'd have to integrate over, because pressure has units of stress. So I'm going to have a pressure force that's the result of all those stress pressure vectors. But where else am I going to have pressure? Earth pressure going up, right? So I'm going to have essentially the same, well, okay. I will have some earth pressures buttressing it. So I've got my overburden, or my sort of bearing down upon, and my buttressing from below. So here's my next simplification. So hold on. So typically call these earth pressure forces. Earth in the sense of soil, not the planet. And here we're going to make that simplification that we're talking about an infinite slope. So sometimes what I'm doing right now is trying to get to is called the infinite slope model. And so we're going to say that the slope, goes, it's the same upslope, it's the same downslope for as far as it matters, so that the earth pressures cancel. Okay. Now in a real world situation, especially if we have a somewhat complicated geometry of a landslide that's more complicated than what I've drawn here, we probably would need to consider those earth pressure forces. But for this, we're not going to worry about it. All right. I'm going to go to erase. What else? Let's start to think about the material that we've got. Yeah.
You have like water pressure inside as well, of course.
Yeah. Yeah, we definitely do. So we've got our pore pressure. And with pore pressure, it gets starts to get really difficult to keep treating this like it's a point mass. But essentially, yeah, if I have a water table in here, then at this potential failure plane, I'm going to have, pressure acting in all directions, right? And what's that going to do? Well, it's not going to affect the weight of the material. In fact, having water in there is going to increase the weight of the material. That's why when I start talking about the density of this, I'll have to talk about the wet bulk density, not dry. But what's that going to do? It's going to do something very similar to what we had with our glacials, our sliding glacier, right? In the case of our sliding glacier, we put in a bunch of water with the spring melt, and we raised the water table in the glacier, and we took some of the bearing of the weight off of the ice and put it into the water. Similarly, in this case, if we were to sort of zoom in here, and look at my bumpy bedrock surface, and actually look at some of these grains. So each of these grains is going to, bear some of that normal force, or some of that normal force is going to be transmitted through the grains. However, once I put water pressure in here, which acts in all directions, right? That's going to take some of that weight off of the grains. Some of that normal force is going to be transmitted through the water rather than through the grain-to-grain contact. And so what's that going to do? That's going to reduce my effective friction. That's what happens with the glaciers. That they jack up the pore pressure enough, and it reduces the friction enough to get the glacier sliding. So the effect then is, since my friction force is proportional to the magnitude of the normal force, well, actually, I should put a caveat on that and put a little effective down here, because in order to get my friction, I have to subtract the pore pressure. Now, writing this is getting a little tricky, but let me just try this way. So the friction then, well, just what I said there. I'll go right in. And now I'm going to dispense with the vectors and the magnitudes. In fact, I probably should have actually doing this right. This would have been a dot product here, right? So the dot product of my effective normal force with the x direction. Here, that gives me the cosine here. Okay, and the negative. All right, so that, I'm gonna wait a minute before I get to trying to write down what this effective normal force is until we dispensed with forces and started talking about stresses. But essentially, we have to subtract the effective normal force is the normal force minus the pore pressure, except we never really say it that way because you can't subtract a pressure from a force. So when we talk about normal stresses, then we can subtract pressure. One more pretty important force. Yeah.
Possibly tension.
Tension, like, what kind of tension?
I guess that kind of implies like what's being layered on top of it, so that might be pressure.
Well, I mean, certainly if we have tension holding, tension that's instead of, so tension versus pressure, right? I mean, tension is really a pressure in some sense, but, pressure we think of pushing things out. Tension we think of pulling things together. So if this soil were wet, but I didn't have a water table, and the water were allowed to drain long enough, then I would have some surface tension in there tending to hold things together. Now, as it turns out, landsliding mostly occurs when things are drenched, and surface tension goes to zero because I've actually got either zero or positive pore pressure. But you kind of are on the right track in terms of, well, I talked about this on Saturday, right? That your typical wicked steep coast range slope is at like 41 degrees, but the angle of repose is like 37 degrees. And so something must be holding it up. What's holding it up? Trees. Trees, but specifically their roots, right? So, and there could be other things too. So cohesion is what we're after. And let me put that we're really after an effective cohesion because we want both the sort of molecular, cohesion due to the van der Waals forces between clay grains or particles, right? So we've got some clay content, and that's going to give it some cohesion due to those van der Waals forces. Those are relatively small, but maybe significant. I already mentioned surface tension. But I also said it's going to go to zero when we want it, right? When we want something to hold things together, surface tension is going to go to zero. In fact, the water pressure, surface tension is a negative water pressure. Our water pressure is going to go positive. So by definition, our surface tension is not a tension anymore. But then, Brendan, you mentioned roots. And roots tend to be a big deal. Now, engineers hate dealing with root cohesion. It's difficult to do it right, and it may not be there when you need it if you're an engineer. So if you're an engineer, then you're going to do your designs without accounting for root cohesion. If you want to figure out whether a dam is likely to hold together, you don't think that roots are going to hold it together. In general, you're not going to count on roots to give you your cohesion. But it's often the difference between life and death in the real world. And I mean that quite literally. So, because if you live downslope of a potential failure, you're really going to care about root cohesion, and so we cannot neglect it. But we should, I will just toss out the caveat at this point that the way we're going to account for it is kind of fake. Because we're not, it's difficult to do it right, but we got to include it. So that's one of our simplifications. It's like, well, we're going to kind of fudge our way through the root cohesion and just go with that. All right, so I've gotten to this point where, like with cohesion and pore pressure, you know, we're really now talking about stresses and strengths, you know, forces per unit area. I can't pretend that I've got a point mass anymore with these vectors on it. I've got to deal with stresses at this point. So let me redraw this, and I'm just going to start over because rather than try to alter what I've got. So again, sloping soil surface, sloping bedrock surface, coordinate system with the x direction parallel to the slope, z direction normal, and y into the board. And now we're going, well, okay, I'll go ahead and again draw some sides on it, you know, sort of to limit my focus to some piece of the pie here, so to speak. Note that I've got some distance, some length of that, however small, in the x direction. We'll go ahead and call that dx, and in the y direction, the distance dy. And all right, what else have we got? I had a water table. Go ahead and draw that back in. All right, I've got some thickness to this soil. We'll call it capital H. Earth material, soil, mobile regolith, what have you. Similarly, I've got some thickness of the water table, which is a bit of an odd way to think about it, but it works. Because it does actually matter in this case whether the water table is parallel to the slope or flat. And in this case, we're going to assume that, well, we are on a slope, the water is moving. It's not, say, dammed up behind some road fill or something like that. You know, again, we're dealing with an infinite slope kind of situation, and so we have water flow parallel to the parallel to the slope, and so our water table has that sort of thickness look to it. All right, if I then consider what are the stresses here at the base of the wedge O stuff, I've got my weight that's pointing towards the center of the earth. Again, I break that up into slope normal, parallel, and slope parallel components. And now instead of a normal force, I have a normal stress that acts opposite and equal to that component of the gravity. And that is represented almost always by a lowercase Greek sigma. Okay, I've got, let me go ahead and say I've got this slope parallel, component of the weight, and that is my shear stress. Now I can really draw in my pore pressure in a meaningful way. And given its effect, even though I know the pressure acts in all directions, for our purposes, it's effectively acting counter to the normal stress. So I'll draw in small lowercase u for my core pressure. We've got material property, wet bulk density. All right. So now that we're full on dealing with stresses, let's deal with the simplest first. The simplest is that shear stress, our driving stress. Well, actually, the simplest is to first point out that that we've got nothing going on in the z direction. You know, that the normal stress counters the weight of gravity in the slope normal direction, and so in the z direction we've got nothing going on. But in the x direction, well, in the positive x direction, we've got shear stress. And that's relatively, that's pretty simple. Because that's just the weight component in the slope normal direction divided by the basal area. And the weight is mass, we go mass times gravity times sine theta divided by dx dy. My mass, now that I've written up that I've got a bulk density and I've put dimensions of this block of material, my mass is simply the wet bulk density times the depth times the dx dy. And actually I should say soil thickness rather than soil depth, just to make clear we're talking about the slope normal direction rather than a vertical depth. Again, dividing through by my dx and dy. Okay, my dx's cancel, my dy's cancel, and I've got this pretty simple form. Where that's my shear stress. Okay, just the bulk density, wet bulk density times the soil thickness times gravity times the sine of the slope angle. And that's it for the positive x direction. The negative x direction is where it gets a bit more complicated. That's where we've got our complicated things like friction, cohesion. Well, specifically friction and cohesion. Like about it. So all right. The friction, let's deal with friction first. Friction is equal to the effective normal stress times my friction coefficient. Let's deal with these things in turn. My effective normal stress. Or be real imaginative, just put a sub EFF on our sigma, and that is going to be equal to my actual sigma that is equal to the slope normal component of the weight of the material, but I've got to subtract my portion. So it's normal stress minus pore pressure. Okay. Normal stress, that part's simple. That's just a lot like my shear stress, right? It's just mg, except instead of sine theta, cosine theta, but and divided by the basal area. And if you'll allow me to skip the belaboring step of writing up the rho b times h times dx dy, canceling out the dx's and dy's, then I can simply write that my normal stress is the wet bulk density times the soil thickness times gravity times cosine of the sloping. The pore pressure also ends up being a bit simple. It is pressure head times water density times gravity. So the pressure head is HW times and this is where it gets a little weird. It's HW reduced by the cosine of the slope angle. Water density, rho W, gravity, okay. And so let me just rewrite that like the rest of the stuff. Okay, so at least it's looking a little bit convenient or familiar in the sense that it mimics the form of the normal stress. So that our effective normal stress is just the difference of the two. So, and I'll go ahead and combine some terms here because I can gather up my G and my cosine and distribute my bulk densities of my soil bulk density, my density of water, my soil thickness, my water table thickness in the parentheses here. Okay. Still not there yet. Because I haven't dealt with my coefficient of friction yet. So let's talk a bit about that, because it turns out, I'm just going to have to erase it. I'm just rewriting. Okay. Turns out friction coefficient is not that hard to measure. I've already talked about the angle of repose, and several people have sort of nodded their heads along. Okay, yeah, I see. So how do we measure the friction coefficient? Well, we do so by measuring the angle of repose. What's the angle of repose? It's the steepest we can pile up the stuff when it's dry. So you'll often, sometimes you'll see, well, okay. So essentially, yeah, if I put up a table and I say my material is sand and I pile the sand on there as steeply as I can, then that angle we'll call phi. And that is my angle of repose, sometimes called the friction angle. And that means that tangent of that angle is the friction slope. And that this happens to be equal to my friction coefficient. Handy that. So that means that finally I can write down my friction. Just give it an F. And say, okay, it is counter to my effective normal stress and modified proportional to this friction coefficient or friction slope. So that means my friction is, well, yeah, here we go. Sigma effective, that's this quantity. So my friction is minus rho BH minus rho WHW. Woo! G cosine theta tan phi. All right. That's my friction. Okay. Took a few steps to get there, but it's worth remembering. So what, let's just look, since it took us a few steps, let's remember what's here. We've got just the basic weight of the material, but we have to subtract off the pore pressure. We've got our friction slope here. That is our friction coefficient. And I've given it a minus sign because I said that it's acting in the minus x direction. All right. Now, finally, cohesion. All right. Cohesion, I talked about all the things that it is. Give it a small c. Yep, that's it. It's hard to measure. Sometimes we effectively measure it by what it must have been for something to not happen or something that did happen. You know, well, if we know everything else, then the cohesion couldn't have been greater than this because it did fail, or cohesion must have been greater than this because it didn't fail. So finally then, my so-called shear strength, which is what's going to act counter to my shear stress, give it a letter S, that's equal to friction plus cohesion. So I've given them both minus signs because they're both acting in the minus x direction. Okay. Finally ready to consider a failure criterion, or a safety criterion. A no-go, a go, no-go decision, as it were. So, the tipping point is when the sum of the shear stress and the shear strength is 0. Right? Or tau equals minus s, or the ratio of minus s to tau equals 1. And this is what we're going to call our factor of safety. And it's just, well, I've erased enough, and now I've got to write it over. Great. Fine. The factor of safety then is just the ratio of the magnitude of the shear strength to the magnitude of the shear stress. Let's write my shear stress first, because boy, this is a lot simpler. And then up here, now, you will be tempted, so sorely tempted to do, if you ever have to do any algebra with this, you'll be sorely tempted to just forget about C because it's making your life difficult. So let me go ahead and write it in a somewhat less simple form, but okay. So I could write this as the sum of this over this and this over this. Okay? You could write it as the sum of the friction over the shear stress and the cohesion over the shear stress. The sum of the friction over this shear stress simplifies quite a bit because I've got lots of common factors. I've got my rho b and h, got my g's, my sine theta, cosine theta becomes my cosine theta over sine theta becomes a 1 over tan theta. So that part actually simplifies out kind of neatly, like so. But cannot ever forget the cohesion because likely it's what's saving our lives. And there we go. Now, worth looking at this for a second in our last minute or so. No, I don't have a last minute according to this clock. But if it's dry, HW goes to 0. And then if I have no cohesion, say I'm just dealing with a pile of sand, then it's stable if the factor of safety is greater than 1. Factor of safety is less than 1, then I have failure. So in the dry cohesionless case, then I have stability as long as my friction angle is greater than my slope angle. Simple enough. Now we know that that's not good enough because we know that my typical friction angles are about 37 degrees for a gravelly sandy loam, and my typical, say, coast range steep slopes are 41 degrees. That's it. So 37 degrees for the friction angle, 41 degrees for the actual slope angle in a lot of parts of the coast range. So again, cohesion, cohesion, cohesion. And that's just, you know, I mean, it doesn't fail when it's dry. It also doesn't fail when it gets pretty wet. So cohesion is pretty big, and we will continue with that next time. There was a question of whether landsliding will be on the midterm, and I think not. Because, yeah, we're not there yet. Yeah?
Tan in the numerator, tan.
That's a feed. I got kind of hurried at the end. The Greek letter P. Phi. That's the angle of repose.